Welcome back, students. So now in this part I will tell you about the photoelectric effect and dual nature of matter. That means I can treat my electron as wave also and matter as well, particle as well, which earlier was only confined up to the particle thing as proposed by Niels Bohr. So now we'll get some examples also where we see that wave nature is getting included. So here let's begin. So now we'll move on to the dual nature of matter and the photoelectric effect, which is the beginning of the modern model of atom, the quantum mechanics model, in which we'll understand the duality nature of electrons. So let's proceed. The dual nature of matter. We'll see that electrons can be a wave and as well as a particle, both nature. In some of the cases, like phenomena of diffraction, interference, it can be explained on the basis of wave character. However, in some of the cases such as black body radiation, photoelectric effect, they are explained on the basis of particle nature. So that's why light is said to have the dual character. The first studies were studied by Einstein, Albert Einstein, in 1905. Then came de Broglie and extended the idea of photons to the material particles such as electrons, and he proposed that matter has also a dual character. Means you can assume, guys, that it's like let me draw it here. It's like a dragon ball. If I'll draw, then say suppose this is a dragon ball, okay, and waves are coming. One second. Let me use different color, guys. Yeah. So suppose this is moving in this direction. Okay. So with the movement, it also emitting waves. Okay. It is moving in this direction. Plus it is also giving the waves. So every matter is of that kind, means every matter has dual character. It is particle nature also and it has wave character also. In this way it was understood, and it added a very, very recent discovery to the modern quantum mechanical model of atom. Okay, this is the latest in the modern concept. So de Broglie, he relate the equations. First of all, this is Planck's quantum theory, E is equal to h nu, okay, and then this is E is equal to mc square according to Einstein. And when he quoted both these two, he got that lambda is equal to h by mc, okay, h by mc. mc is what? That is your p, the momentum. So lambda is equal to h by p. I can write here. What I can write? I can write lambda, that is equal to h by p. Okay. Planck's theory was different. He said that when a black body is heated, means he was giving the laws on the basis of particle nature. Okay. But when he just did this experiment, that a black body radiation, when it is getting heated, then it emits radiations of different wavelength. So he then generalized the de Broglie law also in the presence of absorption or emission of energy. Okay, so that is a small packets or bundle of energy, which he called what? Which he called quanta. Quanta. Plural will be quantum energy packet. Okay, smallest is called quantum. One packet is known as quanta and the plural is quantum. So in case of light, the quantum is known as what? Photon. Again, E is equal to h nu was the equation for that. And a body can absorb or radiate the multiples like h nu is there, okay? So 1 h nu, 2 h nu, 3 h nu. Nu is what? Frequency. F you can also use here. Then J.J. Thomson came and he did a very good, very famous experiment, photoelectric effect experiment, in which he emitted, rays on, say, a metal surface, and electrons, they were getting ejected. So he tried to understand the whole process, the whole phenomena. Like, for example, metals which are having low ionization energy. Of course, you guys know that the one which have low ionization energy, why low ionization energy elements they were preferred here? Because electrons can be easily removed out from those substances, right? Like cesium. So when it was passed by ultraviolet radiations, so electrons, they were ejected like this way. If I'm passing onto this metal sheet, electrons are getting rejected. Okay, so this was the apparatus which he used. This is a voltmeter, this is an ammeter, okay, anode, cathode, and here you apply the photon to this metal surface. And he found that there is something V0, okay? If you apply V0 to it, then your dropping potential will get to 0. That means now you will not be able to see the photoelectric effect. Now no more electrons are getting ejected, okay? And that EV0, that is equal to half mv square. That means there is no kinetic energy of electrons after that. That's why EV0, that is equal to half mv square. Half mv square is what? It is kinetic energy of the electrons. Now, what was the observations of photoelectric effect? So first observation was that electrons, they come out as soon as you provide the sufficient light, okay, which strikes the metal surface. So for photoelectric emission to possible, you need sufficient energy of the light source. Then, of course, you need a sufficient frequency, the threshold frequency which is set. It is very, very important, guys. You will find equations based upon threshold frequency and energy. Also, the frequency, it varies with the nature of the metal. For example, the higher the frequency of light, the more energy the photoelectrons will have, okay? And blue light results in faster electrons than the red light because it has lower wavelength but high frequency. While red light, it is having high wavelength and low frequency. And photoelectric current, when the curve was obtained, then it was seen that it increased with the increase of intensity in the light of same frequency. Okay, so if I have this curve between I and I is the current here and say intensity, okay, so it was directly proportional. Okay, it was directly proportional, and if emission is permitted, that a bright light yields more photoelectron than a dim light of the same frequency. This is of the same frequency I am using. Now here you can see the equation which I was just talking about, guys. E nu is the total energy which is getting provided, and E nu naught energy is getting spent. It is getting spent, okay, just to remove the electron, and the rest will change into the kinetic energy of electron. Okay, so h nu is equal to h nu naught plus half mv square. Even graphical questions may come from these equations, okay. So this is your threshold energy actually, h nu naught. H nu naught is your threshold frequency, and h nu naught is your minimum energy. It is also known as, guys, work function. Okay, let me write it here. Phi, that is equal to h nu naught. It is also known as work function. Sometimes you will see in question. Work function. Okay, work function. So the kinetic energy, guys, of the photoelectrons, it increases linearly with the frequency of incident of light. Again, you can see this half mv square is what? That is your Ke. So I can write Ke, that is equal to h into nu minus nu naught. Nu naught is my threshold frequency. Okay. So kinetic energy increases linearly with the frequency of the incident light. This is the frequency of the incident light. So I hope now you understand how that equation is obtained, okay, and what is the purpose behind that equation. If you have any doubts in this chapter, you can log on to www.askIITians.com. There you can go to our discussion board and you can post your question by choosing your category. You have to select your category and you can post your question here. We experts at Ask IITians will answer to your question or doubts within 24 to 48 hours. So guys, we saw about the dual nature of matter and also we learned equations of photoelectric effect. We understand the concept of threshold frequency, stopping potential, threshold energy. That is our work function. Now in my next part, I'll be telling you about the most recent model of atom, that is quantum mechanical model of atom based upon the wave and particle duality of nature. So stay tuned with me for that.